Okay, so this, yes, today is the 26th. We're on page 141. This is section 2.4, writing proofs. Okay? I'm going to use a bigger marker today because the little ones are running out of juice. So, I want you to know that we're going to start. This one says writing proofs, but we do proofs a little bit later on. We don't get too involved with it. Today, we're on page 141. Today, we are trying to get some highlights of proof, but we're not actually going to do proofs. But I want to talk about what a proof is. A proof, the ones that we're going to do is a pattern to solve or to prove, I can't say prove, to show that a statement is true. Okay? Now, a couple of things that we're trying to prove is a theorem, which is a proven statement. In other words, you have facts that prove it. Theorem is spelled T-H-E-O-R-E-M. I will tell you that I very seldom write theorem. I just write T-H-M. Doesn't mean that you guys don't need to know how to spell it, but just I abbreviate T-H-M. And then we have what we call a postulate. The book also calls them an axiom. Okay, I'll put it in parentheses. We use postulate. A postulate is a statement that is not proven, but is accepted as true. And the reason is we can't find a counterexample. So you guys know what a counterexample is, right? So we can't find it. So it's just proven. So theorems and postulates are different. Okay? Today we're going to talk about postulates. A bunch of them. Okay? They're not proven. We just can't find any counterexamples. Yes?
Wouldn't that be like an hypothesis is false? Or, I don't know.
No. Postulates are a little different. Thank you. Good. I think you might be thinking of back when we said if the hypothesis doesn't make sense, if it's not true, it was just true. That's not. No. This statement is we just can't find a counterexample. Okay. All right. So I'm going to erase this because we're going to look at some postulates today. They're on page 141. And I'm going to write them out because you have to write them out in your assignment. You can't put postulate 2.1. You have to write them out. The reason I have you write them out is not to torture you. It's so that your brain will accept some of the things that you're writing down. You write something down and you're more apt to remember it. So the first one is postulate 2.1, but you can't write that. It says through any 2 points. You can't abbreviate points to PTS. There's exactly one line. There is exactly one line. So anytime I put 2 points out here, we'll call this A and this B, I can draw a line through there. Does that make sense? The next one is 2, 3 through any 3 non-collinear. Now, what's non-collinear mean? Not on the same line. Thank you. Through any 3 non-collinear points, there is exactly one plane. So the points have to be non-collinear. So I have a B, and a to see. And we can draw a plane then around it. Does that make sense? Any questions about that? Okay. Now these might seem, you know, sometimes they seem obvious, sometimes they don't. Sometimes you don't even think about it. Okay? It just makes sense. Okay? Then 2-3, a line contains at least 2 points. A line contains at least 2 points. How many points are on a line? Infinite. But it contains at least 2. There has to be at least 2 points on it. Okay? A plane contains at least 3 non-collinear, oh, I'm going to run out of room, points. Sorry, my writing's not great with this marker, but. And that on page 141, they show a plane. It contains millions of points, infinite points, but it has to contain at least 3 non-collinear. Okay? Now theorem 2.5 says if, maybe I should go back this way, if 2 points lie in a plane, then the entire line lies in the plane. Now that's not true if it's 1 point. If it's 1 point, it could intersect the plane. But if there's 2 points in the plane, and they lie on that line, the whole line lies on it. Okay? Okay, the next one's kind of an important one. We use it a lot. We have 2 lines intersect. You know what intersect means, right? If 2 lines intersect, then their intersection is a point, is exactly 1 point. Now, a lot of people just say 2 lines intersect in a point. That's the postulate. Okay? Now, if 2 planes intersect, they intersect in a line. This is very difficult to graph or to draw. On page 41, they do a nice job of, they can color coordinate. They can make one blue and one green. You can take a look at it there. One way I look at it is 2 walls that intersect. They went on forever. You'd have a line between the 2 walls. Okay? That's the way I look at it. These are all postulates. Okay? These are all postulates. All right? So we can, I'm kind of going out of order from what the book goes, but we can talk about algebra postulates or algebra's properties that work for us. For example, the addition, subtraction, multiplication, and division properties in algebra. They say we can add, subtract, multiply, or divide by any number we want to, as long as we do it to both sides of the equation. All right, let me give you an example of what happens in geometry. Okay, let's say that I have, if line segment AB is equal to line segment CD, right? If we say that those 2 are equal, right? Or we can say they're congruent. I'd like to use congruent because we don't. Then I can add anything to both sides and it stays equal. It stays congruent. In other words, I can add, as long as it's the same thing, so I could add xy to AB, and it would be congruent to CD plus xy. What I've done is I've added this segment and this segment to both sides. Now this is the addition property. This is the addition property of equality. All right? It looks like this. If I was to write it down, I would say the addition property of equality. It means that I can add something. What I've done is take an algebra concept and use geometry. Because those are line segments, correct? So I've converted it to a geometric statement, even though it's an algebraic property. Okay? So does everybody understand multiplication, or addition, subtraction, multiplication, and division properties of equality? I can divide by whatever I want. I can multiply as long as I'm doing the same number to both sides. You understand it? Okay, so then we have some algebra concepts that you were going to say, yeah, that just makes sense, but we still have to talk about it. Every number is equal to itself, right? This is called the reflexive property. The reflexive property. Actually, it looks like this. I have you write it like this. It's called the reflexive property of equality. It says A equals A. Every number is equal to itself. Now you have to start somewhere, right? If a number is not equal to itself, we don't have any basis for anything, do we? Well, in geometry, this is the same thing. Line segment AB is equal to line segment AB. Angle X is equal to angle X. Everything is equal to itself. This is called the reflexive. If you look in the mirror, you see yourself. That's why it's called reflexive. All right? It's a reflection, right? Okay, so then there's the symmetric property of equality. And it says if A equals B, then B equals A. Now, you might say, well, that's the commutative property. Not necessarily. If line segment AB equals line segment CD, then line segment CD equals line segment AB, right? You can flip them. It doesn't matter which side of the equation they're on, they're both equal. Does that make sense? Okay. The next is transitive. And this one is huge in geometry. All right, let me explain transitive this way. Kagan has $5, right? Chinny has the same amount of money as Kagan. Connor has the same amount of money as Chinny. And Kellen has the same amount of money as Connor. How much money does Kellen have? How much? $5. Did I ever say that Kellen had $5? No. Did I ever say Connor had $5? No. Did I ever say Chinny had $5? No, but I transferred the $5 all along, right? So something in geometry that might be this is, I'm going to put it under here. Let's say that line segment AB is congruent to line segment CD, all right? And line segment CD is congruent to line segment EF. Tell me the relationship then between AB and EF. They're congruent. Then AB is congruent to EF. I've transferred the equality all along. I said, well, CD was equal to AB, and then CD was equal to EF. Therefore, AB must be equal to EF. Does that make sense? This is called the transitive property. Then we have the substitution property of equality. It says if A equals B, all right, then A may be replaced by B at any time. If we know x equals 6, right? Yeah. Then I can put 6 in for x anytime I want to. In geometry, if I see an angle and it's 90 degrees, I can put 90 degrees in for it any time. You see how that works? All right, and the last one is distributive. I'm going to be honest with you. The distributive does not get used a lot in, and this is of equality. This does not get used a lot in geometry. The distributive says if we have a times the quantity b plus c, that I can distribute that in, I can distribute the a in to both. And I'll reiterate once again, it does not get used in geometry very often. It does sometimes, but not often. Any questions on all these? So we start out by saying that we can add, subtract, multiply, or divide any number or anything to one side of the equation as long as we do it to the other. And then we start saying that every segment is equal to itself, and if a segment is equal to another segment, then the second segment is equal to the first segment. And then we start transferring, using the transitive property, and moving the equality from one thing to another. Does that make sense? All right. The transitive property is used by far the most in geometry. Okay, so make sure you got a clue at what that is. Okay? Well, that brings me to the famous questions that we have in geometry that sometimes you see on tests that you take. They're called always, sometimes, never questions. Always, sometimes, or never. When students leave school early, they forget to turn in their geometry assignment. Always, sometimes, or never. Sometimes. Right? Okay. Dylan is 7 feet tall. Never. Dylan is 3 feet tall. Sometimes. If he's on his knees, right? And you could probably make an argument, well, he could be 7 foot tall if he's standing on somebody's head, or right? But you see the always, sometimes, never? Okay, let me give you an example of an always, sometimes, never in geometry, because that's really what we want to look at, right? We'll start with this one. If two coplanar, remember what coplanar is, they lie in the same plane, lines intersect. If two coplanar lines intersect, then the point of intersection lies in the same plane. Always, sometimes, never. All right, let's do a vote. How many think it's always? Raise your hand. 1, 2, 2. How many think it's sometimes? Nobody. And the rest of you think it's never. That's the way this works, right? Okay. So we had nobody that said it was sometimes, we had 2 that said it was always, and the rest of you said it was never, right? Well, if two coplanar lines, if they lie in the same plane, then their point of intersection must lie on that. Because if more than 2 points lie on there, so it's always. So the 2 people got it right. It's always. It always has to be on there. All right? All right, let's try this one. Let's see if we do a little better here. Because that is only 2 out of what? 7? 2 out of 7? It's not good. 4 points are non-collinear. All right, 4 points are non-collinear. Means they do not lie on the same line. All right, so how many think always? Raise your hand. Always? Let the record show that nobody chose always. All right, sometimes. Oh, let the record show that. Kagan, what do you got? You got your hand up? All right, 1, 2, 3, 4, 5, 6. All 7 of you think sometimes. You are correct. Sometimes they are non-clear. They could be in the same line, but they don't have to be. All right? Are you getting the hang of it? All right, let's do a couple more, shall we? Oops. Always, sometimes, or never. 2 intersecting lines determine a plane. always, sometimes, never. I got two intersecting lines. I'll draw them for you. Does that determine a plane? Always, sometimes, never. Always, raise your hand. Records show that there is nobody that chose always. Okay? Sometimes. One person. And the rest of you are never. What? The rest of you are never. Well, the answer is always. Two intersecting lines determine a plane. The plane is right around it. Okay? If all their points are on there, they have three non-collinear points, right? Then they determine a plane. All right? We didn't do real good on that, did we? All right, how about this one? Three lines intersect in 2 points. Three lines intersect in 2 points. Try to draw that. It helps if you try to draw. How many think always? Let the record show that nobody raised their hand. How about sometimes? We have 1, 2, 3, 4, 5. 5 raised their hands. That means that 2 said never. Okay? The answer is never. There's no possible way that you can draw 3 lines that intersect in 2 points. No. Okay. All right. You see what always, sometimes, never questions are like. They're kind of tough, aren't they?
Coinciding.
What's that? They could be coinciding, but then you don't know if it's the same one. Okay, turn to page 147, please. Page 147. Page 147. Crap. Page 147. Would you read the directions for 16 through 23, please, Kellen?
Explain how the figure illustrates that each statement is true and state the
Postulate.
postulate that can be used to show each statement is true.
All right, let's take a look at number 16. It says lines N and L intersect at point K. Lines N and L, and you can draw it if you want. Here's, remember we use a lowercase n and we use a lowercase l, okay, and they're cursive, and they intersect at point K. The question says, explain how the figure illustrates that each statement is true. Okay? Okay, take a look at the picture, right? Oh, I'm supposed to be looking at the picture. I just drew it.
It's a quarter.
It's a corner, right? And do they intersect at true at the K?
Yes.
Okay, I'm having trouble seeing it because it's dark. N and I can't find L. It's dark. Okay, and they intersect at K, right? Oh, there's L. Okay. And it says the top edges of the bottom layer form intersecting lines. Lines N and L of this cake intersect only once in a point K. Okay, so what postulate are we talking about? What is it? Let's just give the postulates. Let's not, only the postulates. So we're only going to write the postulates. What postulate is that?
The two lines intersect.
That's right. If two lines intersect, they intersect in a point. Okay, don't put postulate whatever that is. I don't know what that is, but don't put it, just write it out. Okay, so we're only going to write postulate. So when you check your answers with the back of the book, they'll have this stuff about on the cake, you know, but don't put that. Just put the postulate that states. Girls should do better at this because it looks like a wedding cake. So, boys, I don't know if you'll handle this very well. All right. So then let's jump down to 24 through 29. Would you read the directions? Aubrey?
Determine whether each statement is always, sometimes, or never true. Explain your reasoning.
Okay. We're just going to go always, sometimes, or never. We're not going to explain, okay? Make sure the other two that aren't here know that. 24, there's exactly one plane that contains non-clear points A, B, and C. Always, sometimes, or never.
Sometimes.
There's exactly one point that contains non-clear points A, B, and C. Would you read, please, on page 141? Would you read postulate 2.2 for me, Ginny? Yeah, so that is always, isn't it? All right, that is always. Okay, you understand why? Okay. Then we're going to jump to, we're going to do 36 through 42. We're going to state the postulate that each one of those says. And figure at the right, make sure you use the figure at the right. State the postulate can be used to show each statement is true. And then we're going to go to, let's throw out 49. So I'm going to throw out 49. Okay? So we're going to do page, and Ginny, what, can I have you write this up on the board? We're going to do page 147, numbers 16 through 29, and we're going to do 36 through 42. Okay, and 36 through 42, you have to write the postulate, just like the first ones, okay? Pretty much, and I'll give you tomorrow to work on it, okay? Now, next week, do we have a quiz or a test? I don't know, I'll have to look that up. Do you have any questions about, all right, do you have any questions? All right, you can get to work.